Good morning, dear student. In today's lecture, we will discuss the next important chapter of our course CHI 331, that is the reaction of coordinated ligands. So, in previous lecture, we will discuss regarding to the photochemistry. So, in this lecture, we will discuss the second important topic, the second important chapter of the section, that is reactions of coordinated ligands. So, what is this coordinated ligands? The ligands which are attached to the metal shows different types of reaction, and therefore this phenomenon is considered as reactions of coordinated ligands. The reactions of coordinated ligands are classified into two types. So, if you consider, it is reactions of coordinated ligands. Coordinated ligands are classified into two types. One is non-chelate forming reaction. So, no chelate is formed in the reaction, a non-chelate forming reaction, and second is chelate forming reaction. Chelate forming reaction. So, the reaction of coordinated ligands are classified into two types. One is non-chelate forming reaction and another is chelate forming reactions. So, in non-chelate forming reaction, generally the monodentate ligands are involved in the reactions, while in chelate forming reaction, generally polydentate ligands, bi, tridentate ligands are involved in the reaction. Again, if you consider this non-chelate, so we are very much interested in the first type of coordinated ligand, reactions of coordinated ligand, that is non-chelate forming reaction. These non-chelate forming reactions are again classified into two types: non-chelate forming reaction. Non-chelate forming reactions are classified into two types, that is first, that is reactions of non-donor atom, reactions of non-donor atom, and second, reactions of donor atom. So, the non-chelate forming reactions are again classified into two types, that is reactions of non-donor atom and reactions of donor atom. So, generally what is the difference between this donor atom and non-donor atoms? Generally this donor atom having a lone pair of electron, so they can donate the electrons. No doubt both ligands donate the electron, but they are reactions of donor atoms, means they having a lone pairs. So, the ligand which contain lone pair are considered as a donor atom, such as ammonia, water. So, they contain a lone pair on nitrogen and oxygen, therefore they are considered as a donor atom. So, in this case there is no any kind of lone pair on the ligands or the atom which is present in ligands. So, no lone pair is available, therefore it is considered as a non-donor atom. So, reactions of non-donor atom. So, in this lecture we are very much interested in the reactions of non-donor atoms. So, we are discuss in this lecture the reactions of non-donor atom. So, let us discuss the reactions of non-donor atom. Reactions of non-donor atom. So, they does not have any lone pair, okay. So, they are considered as a non-donor atoms. Reactions of non-donor atom. We know that whenever a ligand is attached to the metal, whenever a ligand is attached to a metal, it will forms a coordinate bond with metal. So, it will forms, whenever a ligand is attached or forms a bond with metal, it will forms a coordinate bond. So coordinate bonds means donation of electron from only one atom. So only ligand can donate its electron, and therefore the bond which is formed is called as coordinate bond. When coordinate bond is formed, so first point is what? When ligand forms a bond with metal atom, so it will donate its electron and forms a coordinate bonds. So during formation, the electron distribution, so the first important point is that the electron distribution of ligand get changed. The electron distribution of ligand is changed when it forms a bond with metal atom. The electron distribution of ligand is changed. So this is the first point. Electron distribution of ligand is changed due to change in electron distribution. Due to change in electron distribution, its reactivity is also changed. The second point is very important. So whenever ligand is formed a bonds with metal atom, its electron distribution is changed, and due to the change in electron distribution, its reactivity is also changed. Its reactivity is also changed, and therefore due to the change in reactivity, so as the electron distribution is changed, then reactivity is also changed due to the electron distribution, or electron we can say that the electron distribution, okay. So the electrons are disturbed, or the electronic configuration is disturbed. So in this case the electron configuration is disturbed. So we can say that the electron distribution of a ligand is changed, and therefore due to the electron distribution, or we can say that the electron count is changed. So the electron, after donation of electron to the metal atom, the electron distribution is changed, and due to the change in electron distribution, the reactivity is also changed, and due to the change in reactivity, the ligands get activated. So first, when ligand forms a bond with metal atom, electron distribution of a ligand is changed. Due to electron distribution, the reactivity is also changed. Reactivity of ligand is also changed, and due to change in reactivity, the ligands get activated to attack by electrophile or nucleophiles. So due to change in reactivity, they get activated to attack by electrophile or nucleophile. So we know that electrophiles are electron deficient species. They have affinity for electrons, and the nucleophiles are electron rich species having affinity for positive centers. So this is the important points regarding to the reactions of non-donor atom. Whenever a ligand forms a bond with metal atom, its electron distribution is changed. Due to the change in electron distribution, reactivity is also changed. Due to the change in reactivity, the ligands get activated to attack by electrophiles or nucleophiles. So in this lecture, we will discuss the attack of nucleophile on coordinated ligands. So we are very much interested, that is the nucleophilic attack on coordinated ligands. So we are very much interested, that is the nucleophilic attack on coordinated ligands. So we will discuss this first, nucleophilic attack on coordinated ligands, and in next we will discuss the electrophilic attack on coordinated ligands. So whenever ligands forms a bonds with metal atom, its electron distribution is changed. Due to electron distribution, its reactivity is changed, and due to the change in reactivity, it get activated to attack by electrophiles or nucleophiles. So when a nucleophile attack on coordinated ligands, means the ligands which is attached to the metal atoms, they are considered as a coordinated ligands. So when this nucleophile attack on coordinated ligands, what are the conditions for this nucleophile to attack on coordinated ligands? So we will discuss one by one. The first condition is that the net charge on complex is positive. So the overall charge on the complex is positive, net charge on the complex is positive. In that case, the nucleophile can attack on a coordinated ligand. Second important point is that the other ligands are pi acceptor ligands. Other ligands are pi acceptor ligands. So the first case is that the overall charge on the complex is positive. In that case, the nucleophile can attack on coordinated ligand. Second, other ligands are strong pi acceptors. The third important condition for nucleophilic attack on coordinated ligand is that metal atom is coordinatively saturated. So metal atom is coordinatively saturated, means it has no any vacant site. So the nucleophile cannot attack on the metal atom, it will attack on the ligand which is attached to the metal. So this is the important condition. Metal atom is coordinatively saturated, means there is no vacant sites. So nucleophile cannot attack on metal, it will attack on the ligand which is attached to the metal, that is the coordinated ligands. And the next important condition for this nucleophilic attack is that the nucleophilicity of incoming reagent or the nucleophile, the nucleophilicity is very high. So in other words, in simple words, we can say that the nucleophilicity is very high. So the nucleophile is strong nucleophile. A nucleophile should be a strong nucleophiles. So these are the some important conditions for the nucleophilic attack on coordinated ligands. The nucleophilic attack on coordinated ligands, that is the complex should have a positive charge, net charge on complex is positive, other ligands are strong pi acceptor ligand, metal atom is coordinatively saturated, means there is no vacant site. So nucleophile cannot attack on metal atom, it will attack on coordinated ligands. Then the nucleophilicity is very high. So nucleophile, it is a strong nucleophile. So weak nucleophile does not shows attack on this coordinated ligand. So the nucleophile should be a strong nucleophile. So let us discuss some different examples of this system, that is nucleophilic attack on coordinated ligands. So we are very much interested in the reactions of CO ligands, that is carbonyl ligands. So whenever a complex containing a carbonyl ligand, so this carbonyl ligand is electron deficient, it is act as an electrophile, and therefore a nucleophile can attack on these coordinated CO ligands. So how this CO ligand is electrophile? So we know that whenever a metal atom is form a bond with this carbonyl, so this carbonyl forms a sigma bond, that is it is act as sigma donor as well as pi acceptor. So initially it will donate its electron to the metal and forms a sigma bond. After formation of sigma bond, no doubt when metal atom is there, so there is a phenomenon such as pi back bonding. So pi back bonding is also involved in this case. So this carbonyl donates its electron, forms a sigma bond, and we know that this carbon is also a strong pi acceptor ligand. It will takes electrons from metal atom to its antibonding molecular orbital, antibonding vacant molecular orbital, and therefore the back bonding is also involved. So in this case the carbonyl is terminal carbonyl. So if you consider the another example, that is when metal atom, so two metal atom is attached to this carbonyl ligands, metal atom double bond. So in this case if you consider both the cases, so in this case this carbonyl is terminal carbonyl, so in this case this carbonyl is bridging carbonyl, it is bridging and it is terminal, So in this case both metal atom donates electron, that is pi back bonding. So if you consider the pi back bonding, in this case only one metal atom is involved in pi back bonding. In this case two metal atoms are involved in pi back bonding. So in this case if you consider when the CO ligand is bridging ligand, so in this case two metal atoms act as a two metal atoms are involved in pi back bonding, and therefore this carbonyl is not electrophilic in nature, this is nucleophilic in nature. So in this case the bridging carbonyl is nucleophilic in nature, it is not electrophilic, it is nucleophilic in nature, and therefore nucleophile cannot attack on this carbonyl. So in this case if you consider this case, there is only one metal atom is involved in back bonding. So in this case we consider there is a less pi back bonding, So with respect to this, here there is a less pi back bonding, and therefore this carbonyl is electron deficient. So there is a less pi back bonding and therefore it is electron deficient, and when it is electron deficient then the electron rich species, that is nucleophile, can attack on this carbonyl when it is attached to the metal atom, and therefore this carbonyl shows a nucleophilic reaction, that is a nucleophile can attack on this carbonyl when it attached to the metal atom. So this carbonyl is electron deficient, it is act as an electrophile, and therefore nucleophile can attack on this carbonyl because there is a less pi back bonding with this as compared to the bridging carbonyl. So let us discuss some example regarding to this CO ligands. So CO carbonyl ligands are act as an electrophile. So terminal carbonyl ligands are act as a electrophile. So there is a less pi back bonding, so nucleophile can attack on the CO ligand. So let us consider a simple example, that is in this case if you consider example, that is CrCO by 6. So chromium, having configuration that is 4s2 3d4, or we can write this as 4s1 3d5, anomalous behavior of chromium and copper. So 4s1 3d5, and this carbonyl contribute 2 electrons. So for each carbonyl it contribute 2 electrons, so total 6 into 2, total 12 electrons. So the ligand contribute 12 electrons, and this metal atom having total 6 electrons, so total 18 electron is there. So this is 18 electron species. So if you consider an example of CrCO6, that is Cr, it is attached to this carbonyl and other ligand CO by 5. So this is your 18 electron species. So nucleophile, in this case this carbonyl is electron deficient because the other ligands are also a strong pi acceptor. No doubt other ligands are also carbonyl, but they are strong pi acceptor, and therefore it is electron deficient. So in this case if you consider, a nucleophile can attack on this carbonyl. So for example if you consider a simple nucleophile such as OH minus, hydroxyl ion, okay, reaction with NaOH, then this hydroxyl ion will attack on this electron deficient center carbonyl and we get this. So what you get here, CO by 5, this is your Cr, then this C double bond O, and then there is OH. So when the reactant is 18 electron species, the intermediate is also 18 electron and the product is also 18 electron. So in this case, if we count the electron, this carbonyl contribute 5 into 2, so total 10 electrons, chromium having a 6 electrons, so 10, 6, 16, and this COOH group, acidic group, contribute 1 electrons, so 5 into 2, 10, it contributes 6, 16, and it contributes only 1 electron, so total 17. So this complex have a negative charge to get 18 electrons. So it is 18 electron species. It is 18 electron species, but the intermediate which is formed is highly unstable. The intermediate which is formed is highly unstable, and therefore it will shows agostic interaction. This metal atom, it will shows agostic interaction with this hydrogen is attached to this metal atom. It is highly unstable and it will shows the agostic interaction, means a new bond is formed between this metal atom and hydrogen. So if you consider a new bond is formed, so bond breaking and bond making. So in this case, what you get here, CO by 5, this chromium attached to this hydrogen with elimination of CO2, and if you consider this complex, again it contributes 10 electrons, it contributes 6, this hydrogen contributes 1 electron, so there is a net negative charge on the complex. So this is 18 electron species. So this is the example of nucleophilic attack on coordinated ligands. This carbonyl is considered as a coordinated ligand, means it is attached to the metal atom, but it is electron deficient, and therefore a nucleophile can attack on this electron deficient species, electron deficient center. So we get a intermediate which is highly unstable. So this intermediate, so in this case the reactant, intermediate and product should having an 18 electron species. So the intermediate which is formed is highly unstable, and therefore it will shows agostic interaction with the hydrogen atom which is attached to this oxygen, and therefore finally we get this product, that is CO by 5 CRH having a negative charge with elimination of CO2. So this is the first example. So let us consider the another example of this nucleophilic attack. So if we consider another example, that is MnCO by 6. So if we consider this complex MnCO by 6, so Mn contribute 4s2 3d5, it contribute 7 electron, plus this carbonyl contribute total 12 electrons. So 6 into 2, so total 12 plus 17, 19 electrons. So in nucleophilic reaction, nucleophilic attack on coordinated ligand, the complex should be 18 electron. So in this case the complex is 19 electron, so there is a net positive charge on the complex to becomes 18 electrons. So it is an 18 electron species. This complex on reaction with water, so if you consider OH, water, it is also act as a nucleophile. So if you consider the reaction, that is Mn C triple bond O having positive, and then remaining CO by 5 and having net positive charge on this complex. The reaction with water, that is HOH. So this lone pair of oxygen, it will attack on this carbonyl and we get CO by 5, then Mn here C double bond O, and here the water is attached. So this oxygen having a positive charge. Okay, so in this case we get such a species intermediate, that is a nucleophile. Water, it is also act as a nucleophile, so it will attack on this electron deficient center, that is carbonyl is electron deficient. So after attack of nucleophile on this coordinated ligand, we get this species. So if we count the electron for this species, this carbonyl contribute 10 electrons. So 10 plus this Mn contribute 7 electron, plus this group is attached. So it is attached to, so it will attach to oxygen and this oxygen. So 2, 3. So it will contribute only 1 electrons to the metal, and therefore there is a 1 electron. So total 10 plus 7 plus 1 electron, so total 18 electrons. So this is an 18 electron species. So the complex having no charge. No charge. So this is your 18 electron species. Again, this 18 electron species, the complex which is formed is highly unstable. So in this case also there is an agostic interaction. So if we consider, so to neutralize this charge we can show like that. So we get here CO by 5 Mn C double bond O, and here OH, OH, and then again it is unstable. It is unstable, so it will shows agostic interaction with this metal atom. This hydrogen shows agostic interaction with this metal atom, and then this bond will be formed and this bond will be break. So in this case also we get here final product, that is CO by 5 MnH plus CO2. So removal of CO2. So this species is also 18 electron species. So 10, 7 and 8, it is also 18 electron species. So these are the examples. A nucleophile can attack on these carbonyls. So we will discuss the example of hydroxyl ion, then water, it is also act as a nucleophile. If we consider another example, of, we consider FeCO by 5. So this FeCO by 5, Fe contribute 4s to 3d6. So Fe contribute 8 electrons, and this carbonyl having 10 electrons. So total 18 electron species. This is 18 electron species. So we can write this as Fe C triple bond O having positive and CO by 5. So it is 18 electron species. It is 18 electron species. It will shows, so nucleophile can attack on this carbonyl because it is electron deficient. So in this case, if we consider reaction with sodium borohydride NaBH4, sodium borohydride. So we know that this sodium borohydride is a hydride donor. So in this case hydride H minus, it is act as a nucleophile. So it will use H minus ion, and this H minus ion will attack on this carbonyl. So in this case we get here CO by 5 Fe C double bond O and this H. So again if you consider this complex, it should be 18 electrons. So here 10, it contribute 8. So if you consider this carbonyl contribute 10 electrons, Fe 4s to 3d6, it contribute 8 electrons plus. So this group, that is aldehyde group, it is also contribute 1 electrons. So total 19 electron is there. So net positive charge on this complex to get 18 electrons. 18 electrons. So Fe contribute 8 electrons, this carbonyl contribute 10 electron, total 18, and this aldehyde contribute also 1 electron, so total 19 electron. To get 18 electron, so the complex having positive charge. So in this, the intermediate which is formed, it also shows the agostic interaction. So it will shows the agostic interaction with this hydrogen. So this metal atom, it will shows agostic interaction with this hydrogen, and this bond will form and this bond will be break. So if we see, so in this case also the new bond is formed and this bond will be break. So this bond will be break. So in this case we get here CO by 5 Fe is attached to the metal atom with elimination of CO. So in this case, if you consider this species, it's the carbonyl contribute 10, Fe contribute 8 electrons. So it have a net positive charge to becomes 18 electron species. So Fe 4s2 3d6 8 10 18 and 19. So net positive charge on the complex to becomes 18 electrons. So these are the examples of nucleophilic attack on coordinated ligands. So in this case we will discuss the ligands, that is the coordinated ligand is carbonyl. So we are very much interested in the reactions of carbonyl. Therefore the coordinated ligand in this complex is carbonyl. So nucleophile, that is OH minus ion, water, it is also act as a nucleophile. Then the sodium borohydride, hydride ion donor. So hydride ions are also act as a nucleophile. Then the another nucleophile is CH3Li, that is CH3 having minus charge and Li having positive charge, that is methyl lithium. Methyl lithium, it is also act as a nucleophile. It will also shows the nucleophilic, it will also shows the reaction, that is nucleophilic attack on coordinated ligands. So in the next lecture we will discuss different example which is asked in CSIR NET and SET exam on this topic, that is reactions of nucleophilic attack on coordinated ligands. So we are very much interested in the reactions of carbonyl ligand. We will discuss in next lecture, that is the different examples of this nucleophilic attack on carbonyl ligands, and after that we will discuss the reactions of polines. So we will discuss in next lecture the reactions of carbonyls which is asked in CSIR NET exam and SET exam. So again this is very important topic regarding to the exam, that is CSIR NET and SET exam. Many times the question is asked, it is very easy. So it should understand the basic concept for getting the marks in the exams. Okay, thank you. In next lecture we will discuss the examples which is asked in CSIR NET exam. Thank you once again.